Good morning to all of you. In previous sessions, we have seen different properties of discrete Fourier transform. In today's session, we'll be discussing efficient computation of the discrete Fourier transform. So basically, there are two methods by which we can efficiently compute the DFT, right? So we'll be looking at one of that method that is called as fast Fourier transform, right? So before this, we have already seen the DFT and Fourier transform. Okay, we have seen the Fourier transform can be represented as x of omega, and it can be given by or computed by using formula summation n is equals to minus infinity to infinity x of n into e to the power minus j omega n. But the problem with Fourier transform is that it is a continuous function and it requires more number of computations, right? So therefore we can use discrete Fourier transform, right? So the discrete Fourier transform is denoted as x of k, and the formula for it is summation n is equals to minus infinity to infinity x of n into e to the power minus j 2 pi kn by capital N. So where this capital N represents how many points for which you are computing the DFT. So it can be 2-point DFT, 4-point DFT, 8-point DFT, 16-point DFT, 32-point DFT, and so on. Right? Here, these limits which were from minus infinity to infinity. So these limits will be restricted from, instead of minus infinity to infinity, these limits will be from n is equals to 0 to n minus 1. So therefore it will be computed for only capital N points. So instead of minus infinity to infinity in Fourier transform formula, in place of those limits in DFT, those limits will be from 0 to capital N minus 1. So this is the actual formula for your DFT, j by k n by capital N. So when we were discussing about discrete Fourier transform, we have seen some examples where we have used this formula for the computation of DFT, discrete Fourier transform. Okay, so we have computed the discrete Fourier transform directly by using this formula. Okay, but there are certain methods by which we can efficiently compute the DFT. Okay, so today we'll be discussing this efficient computation of the discrete Fourier transform. Okay, so in efficient computation of the DFT, why it is required that DFT should be computed efficiently, okay, without uh, wasting much more resources of your computational devices, basically, right? So basically DFT, that is discrete Fourier transform, plays an important role in many applications such as linear filtering. Then it can also be used in correlation analysis as well as spectrum analysis, right? Even for performing different image analysis operations, right? So for evaluating discrete Fourier transform in an efficient way, there are two different approaches, right? So as it is used, it can be used in various digital signal processing applications. Okay, you can use discrete Fourier transform in many digital signal processing applications. We can use any one of these strategy for efficient computation of discrete Fourier transform. So first strategy is called as divide and conquer, right? So in algorithmics, right, even in your data structure subjects, right, you might have came across these divide and conquer strategies, right, or divide and conquer algorithms, correct? So in divide and conquer strategy or methodology, uh, any DFT of size n. Okay, this is nothing but again endpoint DFT. So this n is a composite number, right? So this endpoint DFT is reduced to the computation of smaller DFTs. Just for example, if we want to compute 8-point DFT, then it will be reduced to 2 points initially, then 4 point, and then finally the 8-point DFT will be computed, right? So a DFT of size n is reduced to the computation of smaller DFTs, from which the larger DFT is computed, right? So in divide and conquer strategy, we'll be discussing in digital signal processing the strategy which is called as fast Fourier transform. So this fast Fourier transform is categorized under the divide and conquer strategy. So this FFT, so again there are two ways of computing DFT by using FFT. Okay, so first one is the Radix 2 approach, and second one is the Radix 4 approach. Okay, so these are the two strategies that can be used with the fast Fourier transform for efficient computation of DFT using FFT, right? So for computing the DFT, when the size, that is nothing but this capital N, is the power of 2, then it will be referred as Radix 2 approach, and when it is power of 4, then it will be referred as Radix 4 approach. Okay, so if you are using Radix 2 strategy, so the 8-point DFT, okay, so this will be 2 raised to the power 3 will be 8, right? So this 8 is nothing but your n, right? So in Radix 2 strategy, there will be 3 stages for computation of this 8-point DFT. How those 3 stages will be there? So initially 2 points, that is smaller DFT, that is 2-point DFT will be computed, then 4-point DFT will be computed, and then finally this the larger DFT, that is nothing but 8-point DFT will be computed. Just for example, if you want to compute the 4-point DFT using Radix 2 approach, then it will be 2 raised to power 2, right? So there will be 2 stages for computation of 4-point DFT using Radix 2 Fft algorithm, right? So here initially again you will compute the 2-point DFT, then from that 2-point DFT you will compute 4-point DFT. Okay, so there will be 2 stages in 4-point DFT computation using Radix 2, right? But when you are using Radix 4 approach, right, so this 4-point DFT, right, so this will be your 16-point DFT can be computed. If you want to compute the 16-point DFT by using Radix 2 approach, so it will be 2 raised to the power 4. Okay, so it will be 16. So there will be total 4 stages in computation of 16-point DFT using Radix 2 approach. Okay, so it will be initially 2-point DFT will be computed, then 4-point DFT, then 8-point DFT, and then finally 16-point DFT will be computed in these stages. Okay, in case of Radix 4 approach, okay, so if it is a power of 2, power of 4, then this Radix 4 approach can be used, right? But we'll restrict our discussion up to Radix 2 approach, okay, for the computation of DFT, that is endpoint DFT. Okay, so we'll be going into the details of Radix 2 FFT algorithms, right? How it can be used for computation of endpoint DFT efficiently. The second method or approach is called as formulation of DFT as linear filtering operation on the data, right? So second approach for the efficient computation of DFT is formulation of the DFT as a linear filtering operation on the data. Okay, so in this approach there are two algorithms. Okay, first one is the there are basically two algorithms in this approach. So first one is Goldzel algorithm, and second one is the Chirp Z transform algorithm. Okay, so in this second approach, these two algorithms can be used for DFT computation via linear filtering of data sequence. So for that purpose, this Goldzel algorithm or Chirp-Z transform algorithm can be used, right? So these are the two approaches that can be used for the efficient computation of the DFT. Okay, so let's see what this Radix 2 algorithm, because we are restricting our discussion of efficient computation of DFT up to this fast Fourier transform, okay, approach, which comes under the divide and conquer strategy, right? So in case of this Radix 2 FFT algorithm, right, which is nothing but Radix 2 fast Fourier transform algorithm for the efficient computation of DFT. So again, this Radix 2 FFT algorithm can be categorized into two, that is called as DIT FFT, and second one is the DIF FFT. Okay, so this DIT FFT is nothing but decimation in time. Okay, the long form of this DIT is nothing but decimation in time. Okay, and DIF is nothing but this decimation in frequency. Okay, so any one of these two strategies can be used for computation of this uh, discrete Fourier transform. Okay, endpoint DFT, computation of endpoint DFT using FFT algorithm. So what is the difference between this DIT FFT and DIF FFT? Okay, so before that, as we know that the formula for DFT is x of k is equals to summation n is equals to 0 to n minus 1 x of n into e to the power minus j 2 pi k n by capital N. Okay, so this formula can also be represented as summation n is equals to 0 to n minus 1, right, x of n into w in suffix capital N raised to the power k n. Okay, so where basically this w, okay, where this w and k, okay, it's called as Twiddle factor, and it is equals to e to the power minus j 2 pi k by capital N. Okay, so if you are replacing this w and k by this value e to the power minus j 2 pi k by n, so it will be same as this DFT formula. Okay, so we'll be using this Twiddle factor when we are using these algorithms, that is DIT FFT or DIF FFT algorithm for the computation of endpoint DFT using FFT, right? So this is called as what? Twiddle factor, right? So this is nothing but your Twiddle factor. So you have to remember this w and k is nothing but e to the power minus j 2 pi k by capital N, right? Capital N depends on whether you are computing 4-point DFT, 8-point DFT, 16-point DFT. Accordingly, this capital N value will be replaced by 4, 8 or 16 respectively, right? So when you are calling it as decimation, okay, so in case of decimation in time or decimation in frequency, we are basically using the shuffling of the data and bit reversal, right? So just for example, if I am computing 4-point DFT, okay, or 8-point DFT using Radix 2 approach, right? So as it is Radix 2 approach, so it should be 2 raised to the power, so it will be 2 raised to power 2, right? And here it will be 2 raised to power 3, correct? So 2 raised to power 3 is nothing but 8, and 2 raised to power 2 is nothing but 4, right? So when we are computing 4-point DFT, correct, so as it is a binary value, right, because 2 raised to the power n can be used for representation of binary digits. So to represent these 4 points, we will be using 2-bit combination, okay. So 00 can be used for representing 0. So for representation of these 4 points, we will be using 2 bits combination. So 00, 01, 10 and 11. So decimation can be simply viewed as reversing these bits. So if you are reversing these bits, so it will be 00, then it will be 10, it will be 01, and it will be 11. Similarly, in case of 8-point DFT, these 8 uh, bits can be represented by using 3-bit combination. So it will be 000, 001, 010, 011, 100, 101, 110, and 111, right? So these 3-bit combinations we can use. So if you are reversing it, so it will be simply 000, it will be 100, it will be 010, right, it will be 110, this is 001, then again it is 101, then 011, and it will be 111, right? So if I'm considering this as DIT FFT algorithm, right, so it is decimation in time, right? So in 4-point DFT, the input x of n will comprise as 4 samples, right? So it will comprise of 4 samples, correct, in case of 4-point DFT. And if it is decimation in time, then these 4 samples will be your x of 0, x of 1, right? So this is 0 in 1 is correspond to this index, okay. This will be x of 2 and this will be x of 3, right? But if it is decimation in time, then those uh, samples, okay, will be given as input in this order, okay, instead of giving those samples in sequential order as an input to the FFT algorithm. So it will be given in this order as an input. It will not be given as in sequential order. So the first sample that will be applied is x of 0. This 10 is nothing but 2, so it will be x of 2. 01 is 1 and 11 is 3. So this will be given in this order if it is DIT FFT. Okay, so it is for DIT, decimation in time, right? Similarly, you can see this is in case of 4-point DFT. If it is 8-point DFT, so this is your x of 0, x of 1, okay, the sequential order of input sample, x of 2, x of 3, x of 4, x of 5, x of 6, and x of 7, okay. So all these represents the input sample, 8 points specified in the input. right? But if it is dit fft, so again in case of dit fft, your input will be in this order because you are decimating in time. Okay, you are providing decimation in time, right? So your input will be in this order, that is first sample will be x of 0, second will be x of 4, third will be x of 2, then this is x of 6. Okay, as per decimation, this is 2, this is 4, right? This is 6, then x of 1 will be there, then x of 5 will be there, this is x of 3, and then x of 7. Okay, so the input will be applied in this order. That's it: x0, x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, and x of 3, right? So this will be the order of input given in decimation in time, right, algorithm, that is dit fft algorithm. And if you are using dif fft, okay, so decimation will be in frequency. See, when you are performing DFT, what you are doing, so you are taking x of n as an input, and by using endpoint DFT, you are converting it to x of k, which is in frequency domain. So your signal is in time domain, you are transferring it into frequency domain, right? So when you are calling it as decimation in time, so the input will be shuffled, right? Correct, input will be shuffled, that is in time domain, right? We are providing decimation in time. But when you are providing decimation in frequency, this dit is nothing but what, as I specified in the previous slide, it is decimation in time, and dif is decimation in frequency, right? So when you are using decimation in time, then your input sequence is applied as in shuffled form. Okay, so it will not applied in sequential form, but your output will be in sequential form, right? So this for dit fft, input will be in this form, that is x0, x of 2, x of 1, and x of 3, but it outputs will be in sequential form. Okay, so capital X of 0, capital X of 1, capital X of 2, and capital X of 3. Okay, in case of dit fft algorithm. Okay, so your input small x are decimated, but output, that is capital X, are in sequential form, right? Correct. But if it is DIF FFT, so in that case your inputs will be in sequential form, small x of 0, x of 1, x of 2, and x of 3, but output will be decimated because frequency, we are using decimation in frequency, right? So output will be x of 0, then it will be capital X of 0, then capital X of 2, then capital X of 1, and then capital X of 3. So output will be x of 0, x of 2, x of 1, and x of 3. Okay, so input in this case is sequential, samples are applied in sequential form, but output you will get in the decimated form. Okay, so this is decimation in frequency. Okay, similarly in this case, when you are using 8-point DFT, the uh, in case of dit fft, it will be x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3, x of 7. If it is dit fft algorithm, okay, your output in will be in sequential form, so it will be simply capital X of 0, capital X of 1, capital X of 2, capital X of 3, capital X of 4, capital X of 5, capital X of 6, and capital X of 7. When you are using dit fft algorithm, your input will be in this sequence, that is 0, 4, 2, 6, 1, 5, 3, 7, and output will be sequential form, that is 0 1 2 3 4 5 6 7, right? But if you are using Dif Fft, so in that case, in case of Dif Fft, your input will be in sequential form 0 1 2 3 4 5 6 7, but output, that is capital X, will be in this decimated form, that is x of 0, x of 4, x of 2, capital X of 6, capital X of 1, capital X of 5, right? Capital X of 3 and capital X of 7. Okay, so that is what is nothing but the decimation in time and decimation in frequency. Okay, so let's go into more details of it, right? See, in case of your FFT algorithm, okay, we're using computation which is called as basically a combination of butterfly units we are using. Okay, so when we are computing FFT, okay, that is we want to compute endpoint DFT by using FFT algorithm. So for computation of FFT, one butterfly unit is used in each stage. So this basic butterfly structure, so basic butterfly computation in, just for example, DIT FFT algorithm has this structure. Okay, so it has these two parallel lines, right, where you are applying inputs. Just for example, input are A and B, right? Then there will be outputs indicated as capital A and capital B. Okay, so in this case, these inputs are coming as it is here, right? On lower line you will be multiplying it with -1. Here you are using the Twiddle factor for multiplication in the input. So just for example, it is W and K in this case. Okay, so it is W and K we are using. So we name it as this figure indicates basic butterfly computation in DIT FFT algorithm. Okay, so basically how this computation is carried out, we are indicating here. So the same structures we will be using for computation of 8-point DFT using DIT FFT or DIF FFT, right? So here from this point there will be cross line here, right? And here also this same cross line will be there. Okay, so in this fashion it will be coming here, right, these inputs. So at this point from this direction this A is coming, right? It will get multiplied by 1 as there is no value specified here. So here it is 1, it will get multiplied with 1. Here this A plus, okay, these points will compute the addition operation or sum of the inputs which are coming here. So first input is coming from this direction, second input is coming from this direction, right? So here you can see that what value is coming. So B is getting multiplied with this Twiddle factor, that is W and K. So B multiplied by W and K is coming here, right? So the output at this point will be small a, okay, plus W and K multiplied by B. Okay, this W and K will get multiplied by B. Similarly, this A is coming as it is here, right? But the second input to this point is W and K multiplied by B multiplied by -1. So it will be minus W and K B will be there. Okay, so the output B will be A it will be minus, because this -1 is getting multiplied with these two quantities, that is W and K B, right? So this is how these computations are carried out by using this butterfly structure. Okay, so let's go into more details of it. So we'll try to draw the overall computation butterfly diagram for 8-point DFT. Okay, so let's see how it can be performed, okay, by using DIT-FFT. So we're looking at Radix to DIT-FFT structure for 8-point DFT. Okay, so why 8-point DFT? Because when we'll be looking into the examples, when we'll see examples, so maximum will go for the 8-point DFT. Even we can compute the 2-point DFT or 4-point DFT by using these structures, right? So here we are looking at the 8-point DFT, how it will be computed by using DIT-FFT algorithm, right? So as we are computing 8-point DFT, okay, so there will be 8 inputs, right? Starting from x of 0, x of 1, x of 2 up to x of 7, right, as here it has been indicated. So these inputs will be the x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, x of 7 in case of 8-point DFT. Okay, so we'll draw initially 8 parallel lines here. Okay, so we'll draw these 8 parallel lines. We'll just go on next slide to draw this so that it will not be more complicated. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so see, as we are looking for what DIT-FFT algorithm, right? So that means decimation will be in time. Okay, so here it is DIT-FFT algorithm, right? So decimation will be in time, so that means your inputs will be in decimated form. Okay, so what was the sequence for that? So when you are using DIT-FFT, so inputs will be in this order. Okay, a bit reversal order, that is x of 0, x of 4, 2, 6, 1, 5, 3, 7 will be applied. So here it will be x of 0, then there will be x of 4, right? Then x of 2 will be there, right? X of 6, then x of 1 will be there, right? Then x of 5, x of 3, and x of 7 will be there, correct? And these 0, 4, 2, 6, 1, 5, 3, 7, 0, 4, 2, 6, 1, 5, 3, 7. Okay, so input will be these input samples will be applied here. So sample at origin, sample at n is equals to 4, sample at n is equals to 2, and so on, right? But your output will be in sequential form. So here you will get output x of 0, here you will get output x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, and here you will get x of 7. Okay, now when we are talking about the decimation in time FFT algorithm, Okay, we have seen in previous slide the basic structure for it. Okay, this is the basic structure, correct, here, right? So here 1 is getting multiplied with the input, here twiddle factor and -1 is getting multiplied. Okay, so likewise we'll draw these structure here, right? So here 1 is getting multiplied, here this -1 will be there, right? In multiplication twiddle factor will be there, so here w and k, but as it is 8 point dft, so it will be w8. Okay, and the value of k depend on how many input samples you are giving to this structure, right? Correct. So how it will be decided, that I will just tell you. So again here this -1 will be there, as we are looking for computation of what, 8 point dft. So it will be computed initially, 2 point dft will be computed, then 4 point dft, and then finally actual 8 point dft will be computed, right? So again, where there is -1, there will be twiddle factor in multiplication, so it will be w8. So again -1, again -1 will be there, so again here w8 will be there. Okay, twiddle factor, wherever there is -1 in multiplication, the twiddle factor will be there in multiplication. Okay, so here, as per the basic butterfly structure, as we are computing the 2 points, right, dft, so here these outputs will be there, right? These outputs will be applied as an input to next stage. So this is nothing but stage 1 we are looking at, right? So again this will be multiplied. Okay, x of 6 will get multiplied with this twiddle factor, then it will be sent as an input here, right? Another input is coming as x of 2, so x of 2 plus x of 6 multiplied by w8 will be there, right? So likewise these basic structures will be there. Okay, so this is nothing but your stage 1. Here if you look at each these structure, basic structure, so you are here, you are simply computing 2 point dfts. Okay, everywhere you are computing 2 point dfts, but when you are considering 2 point dfts, so sequentially if you look at there, or in this order if you look at there, so inputs are x of 0 and x of 1 will be there, as you are computing 2 point dfts, right? So out of x of 0 and x of 1, only x of 0 is there, right, in case of 2 point dft. So the twiddle factor that you will be using will be w80, right? So everywhere the twiddle factor will be w80, because you are computing 2 point dfts here. So sequentially if you are going for the input, so it will be x of 0 and x of 1. So out of x of 0 and x of 1, x of 0 is there, so everywhere you will go for the twiddle factor w80, right? Similarly in stage 2, okay, you will compute 4 point dft. Okay, so how those dfts will be computed, so these 4 inputs will be taken for computation of 4 point dft. Okay, so there will be 2 dropping lines, right? So this is the first one, this will be second one, right? So to these lines, this -1 will be in multiplication, as well as at input uh, this output will be coming here, but to these lines again twiddle factor will get multiplied, so w8 will be there and w8 will be there. Okay, so two twiddle factors here, only one twiddle factor has been utilized, so here two twiddle factors will be utilized. Again this will be like this. Okay, correct. Okay, so whatever outputs you are getting here, that will get multiplied with these Twiddle factors, right? Then it will get multiplied by -1. Then here it will get sum with this multiplication result will get sum with whatever results that you are getting from these lines, right? Okay, so in this manner, this second stage will compute 4-point DFT. As you can see that 4 points are there. Okay, and if we sequentially write these 4 points, so it will be x of 0, x of 1, and x of 2, x of 3, right? It will be in sequential manner. Those 4 points will be there: x of 0, x of 1, x of 2, x of 3. But out of those 4 points, x of 0, x of 1, x of 2, and x of 3, only x of 0 and x of 2 is there, right? So this Twiddle factor will be W80 and W82 will be utilized in stage 2, right? Why we are using W82 and W80? What is the reason? Because out of, if I am computing 4-point DFT, the sequence of samples will be x of 0, x of 1, x of 2, x of 3, right? But out of these 4 sample, x of 0 is there and x of 2 is there, not x of 1, right? In sequential form. So I'll be writing or using Twiddle factor W80 and W82 there. We have seen that this Twiddle factor, that is W and K, is nothing but what you are computing it as e to the power minus j 2 pi k by n. Okay, when you are computing this Twiddle factor values. Okay, so it will be e to the power minus j 2 pi k by capital N simply. So e to the power minus j 2 pi k by capital N. So here if it is W80, so it will be simply 0, right? E to the power 0. If it is W82, okay, the value of n is 2 and value of, sorry, the value of n is 8 and value of k is 2, so it will be e to the power minus j 4 pi by 8. Okay, so it will be minus j pi by 2 simply, right? So similarly the remaining structure will be again drawn as it is. Okay, same structure will be repeated on following line. Okay, on dropping line you will be multiplying it with -1, okay, as well as with the Twiddle factor, that is W80 and W82, right? So where there is Twiddle factor in multiplication, -1 will also be there on the same line. Okay, so likewise we'll be drawing these structures, right? Okay, so here at stage 2 the 4-point DFTs are computed, and at last stage the final 8-point DFT will be computed. Okay, so how this will be drawn then now? So you will, okay, so these 4 dropping lines will be there. Input coming to these lines will be this one. Okay, output of these points, correct? Again it will be this dropping line, and finally this will be there. Okay, so again where there is dropping line, so -1 will be there in multiplication, and along with -1 there will be Twiddle factor in multiplication. So again it will be W8, then here it will be again W8, here it will be again W8, and here will be again it will be W8. Okay, but which Twiddle factors will be used here, right? So as we are computing 8-point DFT, so all 8 points will be used in sequence. If I am writing in sequence, so x0, x1, x2, x3, then it will be x4, 5, right, 6 and 7 will be there, x of 7, right. So all these points will be there. And if you consider these 8 points, so all these points are there, x0, 1, 2, 3, all these are there. So we'll take this Twiddle factor in that sequence. So w80, w81, w82 and w83 will be there sequentially if we are writing, right. So w80, w81, w82 and w83, these Twiddle factors will be utilized there, right. And from these points again you will be joining these lines, right. So the here this final value of your x of 0, okay, dft sample value, that is x of 0, you will get at this point, right. Similarly here you will get x of 1 value, right, at this point. Whatever outputs are coming here, those will be applied here, right. Then here you will get the x of 2 value, and here you will get the x of 3 value, right. Okay, so these are the, here you will get x of 4, here you will get x of 5, here you will get x of 6, and finally here you will get x of 7, right. So likewise this is the butterfly diagram for the what 8-point DFT. Okay, and if you want to compute the 4-point DFT, okay, if you want to compute the 4-point DFT using Dif algorithm, okay, so this diagram can be simply modified as uh, these 3 stages will not be there. In that case only 2 stages will be there, right. So if 2 stages will be there, I will not redraw this diagram, I will simply indicate here. I'll use some other color so that you will be able to observe it. Okay, so I'll use yellow. Okay, so in case of 4-point DFT, again it will be Dif algorithm. If we are talking about Dif algorithm, so the diagram that you will be using will comprise only these 2 stages up to this point. Okay, so this will be for what, 4-point DFT, because we are interested in only computation of 4-point, so only 4 points will be utilized there, right. And it will be applied in the fashion as we have seen in case of 4-point DFT. So first will be x of 0, then 2, then 1 and then 3. Okay, 0, 2, 1, 3 will be there. Okay, so it will be x of 0 in input in place of x of 0, 2, then x of 2, x of 0, 2, 1, 3, 0, 2, 1, 3, x of 2, x of 1 and x of 3 will be there in this place, right. Okay, and output will be in sequential form. Here you will get x of 0, here you will get x of 1, here you will get x of 2 and here you will get x of 3. Okay, and what about Twiddle factors? Okay, so as it is 4-point DFT, in place of 8 there will be 4 value. Okay, and in this case this Twiddle factor will be w40 w40 in stage 1, but in stage 2 as you can see all 4 points are there, that is 0, 2, 1, 3, so it will be written in sequential form. So 0 and then in place of 2 there will be value 1, so 0 4 sorry w40 and w41 will be the Twiddle factor in stage 2 in case of 4-point DFT. Is that okay? So remaining diagram there is no need to draw, but if it is at point DFT, so this complete diagram should be drawn. Okay, so this is nothing but Dif algorithm. When we'll see the example using this Dif algorithm, so it will be more you will get more understanding of it. But before closing today's session, we'll see the Dif Fft diagram also, right? So in case of Dif Fft, again you will again I will go for this 8-point Dft using Dif Fft algorithm. Okay, so this is for DITFFT. Okay, now we'll draw it for DIFFT. So again, as we are going for 8-point DFT, so 8 parallel lines you will draw. Okay, so these 8 parallel lines will be there. As decimation is in frequency, so input will be in sequential form: x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, x of 6, and x of 7. Okay, there is no decimation in time, it is decimation in frequency. So input, that is time domain signal, will be in sequential 0, 1, 2, 3, 4, 5, 6, 7. Okay, here the decimation was in time: x of 0, 4, 2, 6, 1, 5, 3, 7. Okay, while output was in sequential: x of 0, 1, 2, 3, 4, 5, 6, 7. Now if I'm going for decimation in frequency, so the output will be in decimated. X of 0 will be there, next x of 4 will be there, right? Then 2, 6 will be there, that is x of 2, then x of 6, after that x of 1. Okay, 5, 3, 7, x of 5, x of 3, and x of 7. Okay, so output you will get in this order, that is x of 0, x of 4, 2, 6, 1, 5, 3, 7. See, when you are providing this decimation in frequency, okay, so simply what you had to do, this stage 3 structure. Okay, so this was stage 3 structure, so this stage 3 structure you will draw at stage 1, right? Stage 2 structure will be same, and while this stage 1 structure you will draw at stage 3 when you are using DIFFT algorithm. Okay, so again there will be 3 stages: stage 1, stage 2, okay, and stage 3, right? So only the difference is that this stage 3 structure will be at stage 1, stage 1 structure will be at stage 3. Instead of multiplying these Twiddle factors at input, those Twiddle factors will be multiplied at output. Okay, so that is the only difference in the DITFFT and DIFFT algorithm. So let's try to draw it. So we'll initially draw here the stage 3 structure. Okay, so as per the stage 3 structure, here your dropping lines will be there, right? So here it will be, then second, then third, and then this one will be the fourth one. Okay, so wherever there is dropping line, it will get multiplied with -1. Okay, so we are drawing this stage 3 structure at stage 1 in case of DIFFT algorithm, right? So wherever there is dropping line, it will get multiplied with -1. Okay, and then here it will be these lines. Okay, so wherever there is -1, it will get multiplied with Twiddle factor, but here these Twiddle factors are multiplied in input. Here we have to multiply it in output. Okay, So same Twiddle factors we'll be using, that is W80, then W81, then W82, and then finally W83 will be there. Okay, in output. The stage 2 structure will remain same. Okay, so here the stage 2 structure will be there. And dropping lines, you are multiplying -1 and the Twiddle factor, so it will be W80 and W82. Okay, so same Twiddle factors where we are using, which we are used in the Fft algorithm. Okay, so this is stage 2 structure. Then again in stage 3, the stage 1 structure will be drawn, right? So here -1 will be multiplied in output, W80 will be there. So same structures you have to repeat. So this is how this Dif Fft will be used, right? And this is for 8-point Dft. Okay, and if you are going for 2-point Dft, then in that case only this much portion you have to draw, right? This one only two two stages will be there, right? You have to apply the inputs in sequence, that is x of 0, x of 1, x of 2 and x of 3 will be there. Twiddle factors will be W80 and W81 will be there, right? And output will be in what, decimated form. Okay, so how these outputs will be 0 2, so output will be 0 2 1 3, right? So in case of 4-point Dft, outputs will be x of 0, x of 2, x of 1 and x of 3 will be there in this form. Okay, see the difference only is there in the Twiddle factor. So in place of W80, here W40 will be there, right? Here also it will be W40 and here it will be W41 and W40 will be there, right? So see, we have seen these two approaches, that is DITFFT and DIFFT, correct? So when you are going for DITFFT, the Twiddle factors are in multiplication in inputs, right? So here these Twiddle factors are multiplied in input. Initially 2-point Dft will be computed, then 4-point, and then finally 8-point Dft will be computed, right? The difference between DITFFT and DIFFT: in DITFFT inputs are in decimated form while outputs are in sequential form, right? So outputs are in sequence 0 1 2 3 4 5 6 7, inputs are in decimated form 0 4 2 6 1 5 3 7, right? While in case of DIFFT, inputs are in sequential of 0 1 2 3 4 5 6 7, while outputs are in decimated form. Another difference is that here in stage 1 you are computing 2-point Dft, stage 2 4-point, and in stage 3 8-point Dft. While in case of DIF, this stage 3 structure will be drawn in stage 1, while stage 1 structure is drawn in stage 3, as well as the Twiddle factors which are in multiplication at input. Okay, in case of DITFFT, So these Twiddle factors are in multiplication in output in case of your what you can say Dif Fft algorithm. Okay, so these Twiddle factors are multiplied in outputs. Okay, so in next session, in today's session, what we have seen that you can compute endpoint DFT efficiently by using divide and conquer strategy or by using formulation of DFT as linear filtering operation on the data. In divide and conquer strategy, we can use fast Fourier transform for efficient computation of DFT. So there are two approaches, that is Radix 2 and Radix 4 approach. While in case of formulation of DFT as linear filtering operation, there are two algorithms, that is Gold-Cell and Chubb's head transform. Right. So here we have discussed the Radix 2 FFT algorithm. So that Radix 2 FFT algorithm can be categorized into DIT FFT and DIF FFT algorithm. When you are using decimation in time, so decimation in input sequence will be utilized. When it is decimation in frequency, so decimation in output will be there, right? So for computation of DFT, we are using this basic butterfly structure in case of FFT algorithm. So this basic butterfly structure will be used for computation purpose, where we are using the Twiddle factor. Okay, so for 8-point DFT computation, this is the FFT algorithm and FFT butterfly structures that will be utilized for the efficient computation of DFT, and this one is for the decimation in frequency FFT. Okay, so in this session we'll be discussing some examples how to compute these FFTs, that is DIT FFT and DIF FFT, or how to compute DFT using DIT FFT and DIF FFT. So some examples we'll be discussing in next session. Thank you for joining this session.